And first of all, we're going to talk about what is the rate law. So the rate law is the mathematical relationship between the rate of the reaction and the concentrations of the reactants. And remember, we do everything with respect to the reactants, pretty much because we had to make it a universal way that everyone would agree on, and we decided reactants. So everything is with respect to the reactants. And the rate law is determined experimentally. Okay, I'm going to say this a few times today. You cannot determine the rate law based on the chemical reaction. It is determined experimentally, not based on the chemical reaction or the balanced chemical reaction. The rate of the reaction is directly proportional to the concentration of each reactant raised to a power. So the powers are called the orders. So this is raised to the order n, raised to the order m. Remember, these little brackets, these mean molarity. Molarity. Remember molarity? Moles over liters. Like, think everything we've been doing in experiment 9, molarity. So N and M are the orders. And so what we're going to be doing today is we're going to try and figure out what K is, but we're going to do that by figuring out the order of the reaction. And again, this is determined experimentally. We cannot determine the order of the reaction based on a balanced chemical equation. Now, saying that, I kind of picked a bad example here, but this is just by chance. So the exponent on each reactant in the rate law is called the order. And so how we say this is, for example, this is the experimentally determined rate law. It just happens to be these coefficients, but this is not where it came from. So I said I did picked a bad one. So this is the rate law for this reaction. And we're going to talk about how we use this in the next couple of lectures. And so how we use and say this reaction. So this, it means second order, and this is first order. So we don't write the one, but we understand it as a first order reaction. And so we say that this reaction is second order with respect to NO. And this is first order with respect to O2. And then this is a 1. The overall reaction, the overall order, this is a third order overall. So the overall, we just add these exponents. So if this was also a 2, then it would be a fourth order reaction. Now, these are usually 0s, 1s, or 2s, but they can be fractions. They could be negative, they could be positive. We'll try to save some whole numbers mostly today. When we talk to each other again on Thursday, we'll be doing all sorts of crazy stuff. Now, a 0 order reaction, you won't see the reactant in here because if you raise anything to the 0, it's 1. And so if this was 0 order with respect to O2, you would just see this. This would be your rate law. So if it was 0 order with respect to O2, you just wouldn't write it in here for 0 order. So we're going to see a couple of these and we're going to practice with these today. Okay, so let's just do some like basic practicing with these. So the rate equation for the reaction of NO with ozone is this. And so you can see here, this means this is first order with respect to NO. This is first order with respect to O3. The overall order of the reaction is 2. Right? And so this is our rate law. Again, determined experimentally. So if the rate, I think I'm just going to write this whole thing over again so you can see what all these things mean. So I'm just writing this down here just to make it bigger so you can see it a little bit better. So you understand how this works. So I just rewrote this. So the rate is this. The concentration of NO, right? It's molarity. That's molarity, NO. And then O3 is right here. And so what they want is calculate the rate constant. Rate constant is K, right? So they want us to calculate K. So they're giving us rate. They're giving us this, they're giving us this. We just need to rearrange and solve for K. Now, really nicely, these are both to the 1. So all we have to do is plug them in, right? So it's Not such a crazy problem. And these Ks, as long as, so as we talked about last time, the rate constant K doesn't change, right? And we're going to actually look at that today. It doesn't change. As long as we don't change the temperature, it doesn't change, right? And so as long as we don't change our temperature, K never changes. And the third day of our lab, we'll be changing some temperatures. And then, so our goal is to find K. Okay, so here's our rate. And then we're gonna just solve for K. So when you solve for it, the numbers here sometimes get a little wacky, but it's just math, right? So we wanna divide by NO and O3. So it's rate divided by NO times O3, right? That's where we get our equation. We just rearrange it. So K equals our rate, 6.60 times 10 to the negative, that's not a 6 molarity per second over NO, which is 1 times 10 to the negative 6 molar, times O3, which is 3 times 10 to the negative 6 molar. And now you'll see there's like some wacky little units here. So this M, let me just, I'm going to change the way I wrote this. So this M/S, this slash is the same as this right here. So I did this with gas laws with you guys a couple times. So M/S, that's the same units. And so you can see like this M crosses off with this M, but we still have an M and an S. So our units end up being 1 over M times S. By the way, Ks have crazy units. Like you're going to see crazy units. So that would be the same thing as M to the negative 1, S to the negative 1, right? So those are our units. So when we put this in our calculator, we get 2.2 times 10 to the negative 7th. And then those are our, I'll just say 2.2 times 10 to the negative 7th. And our units are M to the negative 1, S to the negative 1. Be prepared for crazy units for K. Like you're going to see, they get crazy. Okay, so this is just rearranging the math and plugging everything in. So really this question is, do you understand what everything means? Like rate, K, rate constant, things of that sort. Okay. So as promised, everything is much neater here. And here's our wacky kind of rate constant units. All right, so let's try another one of these. Actually, I'm gonna have you try this one, but I'll help you set this up. Maybe I'll just help you set this one out. So this one says the rate law for the decomposition of acetaldehyde is K equals acetaldehyde squared. What is the rate of the reaction when the concentration of, so when you see these little brackets right here, that means concentration of whatever's inside. And concentration is always in molarity, right? So this means concentration of acetaldehyde. And the rate constant is this. Remember, rate constant is K, right? So it's saying that is K. And here is our reaction. And so just think of it as rate equals K times, I'll just say ACE squared. And this question is asking, what is the rate of the reaction? So it's asking for this. Right? Okay, so I'm going to give you like a minute or two. Try to do this problem just so you can see how everything goes in. You got to have your calculator near you, and then type your answer into the chat and see if you can figure out those units too. That always ends up interesting. Okay, so I'm going to give you a minute or two to try this one, and then we're going to do it together. And even if you're watching this later, or if you're like, oh, where's my calculator? Get your calculator, trust me. You're gonna want your calculator during this entire lecture. If you don't have it now, grab it because you're definitely going to need it. All right, so try this now, and then we're gonna go over this together. Okay, so I'm seeing a few of these already. All right, so when we put this in, right, we're looking for our rate. So here is our equation. We're just solving for our rate, no need to rearrange. And we put this in and our units end up kind of nice, right? It ends up just being molarity per second. Because remember, this is squared here. So this unit is like molarity times molarity. So one of these crosses off with one of these. So we still have this one. And we still have this one. Kind of looks weird when I put all three of them there. So it's molarities per second. Or you could say m times s to the -1. This is the same as this unit. You'll see rates and k's. It's some crazy, crazy units. Okay, any questions on this one before we move on? All right. Now we're going to do what's called initial rates. Very different than what we did before. So pay very close attention. This is what you're going to be doing for your pre-lab that's due today. This is also what we're going to be doing during our lab on Thursday. We're actually going to be experimentally determining the rate law. So we're going to actually do experiments in lab. So again, the rate law shows how the rate of the reaction depends on the concentration of the reactants. And so changing the initial concentrations of a reactant will affect the initial rate of the reaction. So in lab, we're going to be changing the initial concentrations of reactants. And then from that, we're going to be figuring out the rate of the reaction. Okay, so let's just do a really generic reaction. A goes to products. So you can see here, in this specific example, here's our rate, and here's our concentration of A in molarity. So you can see here that when we doubled, so let's just start here. So my concentration was 0.01, here is my rate. Then I doubled it to 0.02, here was my rate. Do you see how when I doubled my concentration, nothing happened to my rate? It stayed the same. So even though I increased the concentration, the rate did not change. Now, let's look at another one. Let's pretend it's a different reaction. This time, again, I doubled the concentration.
Oh, yeah?
And then if you see
sorry.
here, no problem. So you see here, the rate doubled also. So what we're going to be doing in lab and what we're going to do, this is called the method of initial rates, is we're going to be changing the concentration and then seeing how does that affect the rate of the reaction. And from there, we're going to find our rate law. Another possibility, and this one can be a little bit harder to see. Here we are again, we doubled our reactant, and this time, so this went up by 2, this time it went up by 4. And so when these things happen, we can figure out the order of the reactions. And I'm going to go all the way back to the first one. So you can see. So in this one here, so we doubled this, no change. This is called a zero order reaction. So this one would be zero order. So we doubled our concentration, but nothing happened to our rate. We call that zero order. This one here, again, we doubled this, and this also doubled, or it was proportional. So whatever we did here, the same thing happened with the rate. This is a first order reaction. Our next one, we doubled this, but this went up by 4. This is a second order reaction. So here's our rate law right here. There's our rate constant. That's the concentration of our reactant, and that's the order of our reaction. If a reaction is zero order, the rate of the reaction is always the same. So when we double A, nothing happens to the rate. In a first order reaction, it's directly proportional. So if we double A, we double the rate. If we triple A, we triple the rate. So it's directly proportional. Whatever happens to A also is reflected in the rate of the reaction. A second order reaction, the rate is directly proportional to the square. So if we double A, we quadruple, we double this, this goes up by 4. So we're going to be used. So I always tell people this is like this is one of those star highlight things. Until you get used to these things, star highlight this one because you're going to come back to it a bunch. Okay, so now what if there's multiple reactants, which like there pretty much is always multiple reactions or reactants. So if we change the reactant, it will affect the overall rate of the reaction. So by changing the initial concentration of one reactant at a time, the effect of the reactant's concentration can be determined. So what does that mean? We hold one reactant constant and only change the other one. Therefore, any change in the rate of the reaction must be due to the one that we change. So in examining the results, we compare the differences in the rates for the reactants that only differed their concentration of one reactant. And again, this is exactly what we're going to be doing in our lab. All right, so let's look at what am I talking about here? So here's an experiment. We did the experiment 4 times. You can remember when you were writing the procedure for your lab, I think we're doing ours like 8, 10 times. We're doing it a bunch. So the first time we did the experiment, we had, so here's our reaction. And again, we always do it with respect to the reactants. So we had 0.1 molar NO2 and 0.1 molar CO. So they were the same. And our initial rate was this. Then we did the reaction again. This time we kept CO the same and doubled NO2. Right? Now, why did we do that? If we keep this the same, then any change we see in our rate must be due to the change in NO. And we're going to be doing this, as you read in your procedure, plenty of times. Then we did the experiment a 3rd time. And again, we kept them the same here. And you're going to see, and then we did it a 4th time. We quadrupled this and left this one the same. Okay, and then each time, we measured the rate, we measured the rate, we measured the rate, which you're going to be doing by timing it and then calculating the rates. Okay, so our rate law, our generic rate law is always the same. It's rate times K times concentration of reactants. What this order is, don't know. How we're going to figure that out is from here. That's what we're going to be doing. Okay, so we're going to examine the data and figure out which ones we're going to use. Okay, so let's decide, I don't know which ones we want to use first. So if we want to figure out the rate, this N, so let's figure out N. So we want to figure out N. Then we want to look for changing this, but keeping this the same. All right, so we want to change NO2, but not CO. So we kind of look, well, this changes. These two can't be these two, right? Because these two are the same. So it can't be that one. So it could be comparing 1 and 2, or it could be 2 and 4, right? We have a lot of options here. But remember, we have to keep CO the same. Well, here, CO is the same between 1 and 2, or between 2 and 4, it's the same, or between 1 and 4, it's the same. I just say, I always start at the top. Let's use 1 and 2. Why? This is the same. This doubles. Makes my life so much easier. So you can actually do this from inspection here. And you can actually see that this goes up by 2. Oh yeah, see, look, that's better. Now you can see that I use this one. So this one goes up by 2. And this one goes up by 4. So this would be a 2nd order reaction. Now, let's say you're like, I don't know, I didn't really see that. So I'm going to show you how you can do this. So what I did I'm going to show you how you can do this, what's called by inspection, and then I'm going to show you the math. Some of you are going to prefer to do this by inspection, which means really just looking at it and it just kind of jumps out at you. You can always do that. Well, 95% of the time. Sometimes you're going to have to do the math. Some of you are going to be like, I can't see this. I'm going to show you how to do the math. Okay, so what does it mean by inspection? So what we did was we compared experiment 2 to experiment 1. And you can see it doubled, right? From 1 to 2, it doubled. And then we look here from 0.8, this one went right 2.82 to 2.1. This one quadrupled to 4. So remember, when that happens, when this doubles and this goes up by 4, it's going to be a second order. Sorry, prepare for my dogs to bark. That's what they're like. Okay, so now let's say you're like, I did not see that. I'm going to show you how to do the math, which I need to get rid of all this, how you can do the math here. Okay, so here's how you can do it with the math. So we're going to do the second one over the first one. Now, if at any point here this confuses anyone, please, please, please stop me and ask questions. So here's our rate law. Rate equals K times NO2. Trying to write this really neatly, to the N times CO to the M. I don't know why we use N and M. You can use X and Y, it doesn't matter what you use. So we're going to do 2 over 1 here. Trying to leave myself enough room. So we're going to do experiment 2 over experiment 1. So what we're trying to do is we're trying to figure out what is the rate with respect to NO2 here. So this one doubled, this one stayed the same. Okay. So all you do is you put 1 over the other. So when we do that, we take experiment 2. See, there goes my dogs. Here's experiment 2, and I'm just going to write experiment 2 here. So the rate of experiment 2 is 0.0082 equals K times NO2, which is 0.2 to the N, I don't know what it is, times this one, which is 0.1 times the M, right? NO2 times CO. And here's where I got those numbers. Then I take that whole thing and I put it over number 1. Right here. My rate is 0.0021 equals K times, again, my NO2, right? Because I'm doing this one right here. 0.1 to the N times this, this one's the same, 0.1 to the M. And so you see how this one's held constant right here? This is held constant. So when I divide this, it just goes away. So you don't even need to write it. And that's literally the whole purpose of grabbing one where this doesn't change, because any change in this rate here has to be due to the change in these concentrations, because these cancel out. Okay, now when we do this math, you get 3.9 equals, and then when you divide, so when I divided these two, I get 3.9. And when you take 0.2 divided by 0.1, you get 2. Just put that in your calculator. And it's to the N. So this is our equation right here. 3.9 equals to the N. Now, those of you who have not been in log math or done log math in a while, you take the log of both sides and you bring your N down. So to solve this one, oops, let me show you how to solve this. So when you solve this, we take the log of both sides. So we take the log of 3.9 equals, and then N log 2. So your N comes here, log 2, just in case you don't remember. And again, we're solving for N. So we're just going to divide by log 2, divide by, doesn't really look like a 9, divide by log 2, and you get n equals 1.96. Well, that's close enough to 2. Second order reaction. So this math way, you can always do the math way. You can also do it by inspection. Again, what does by inspection mean? Okay, well, I look at this and I see, oh, that went up by 2. And then I look at this and I say, oh, that went up by 4, quadrupled. This is a 4, this is a second order reaction. And so you could have just said, I know this is n is 2. I know it's second order from inspection, or you can do the math. Either of these ways will work. It just really depends on which way your brain likes. Okay, any questions on that? So what we figured out, the book, sorry, I'm just reading a question. Oh no, it doesn't matter. Oh, someone questioned. So the book has M here and N here. Yeah, it doesn't matter. You can call it whatever you want, X, Y, whatever you want to call them. Doesn't matter. I just call them N and M. Okay, so now what have we figured out? So here's our rate law, right? So this is what we figured out. We figured out that the rate equals K times NO2 to the second, CO to the, we still don't know. We gotta find CO now. Okay, so I gotta erase all this. So here's our, we figured out with our NO2 that our rate law. Here's the same thing that I just did with the math. I did all the math and you end up here. Here's when I do all the math. Okay, so we figured out that it is what we call second order with respect to NO2. But now we need to figure out CO. All right, so this time we want to hold NO2 the same because we want any change in these rates to be due to CO. So can't be that one, can't be that one. We only have this choice. This is the only choice when NO2 is the same. So we have to use 2 and 3 here, have to. So we look what happens here. So this goes up by 2. Oh, and this doesn't change, right? So this doesn't change. So this is a 0 order reaction. And again, I'm doing this by inspection. If your concentration doubles, but your rate doesn't change, that's a 0 order reaction. So what's our rate here? Our rate is K times NO2 squared times CO to the 0. But remember, this is 1. So our rate is just dependent on NO2. It doesn't matter what concentration we have CO, it's not going to affect the rate of a reaction. So this one's kind of easy to see. No change. But let me just do it with the math just one more time so you can see how this works. So if I'm going to do experiment 3 over experiment 2. So I do my rate. So I'm just writing my whole rate law, which is 0.0082 equals K times 0.2 to the M. And I'm not even going to write this one this time because I showed you how it just disappears. Over experiment 3, 0.00. Sorry. You do 3 over 2, 8, 3, 8, 2. Doing this one on the top. This one is going on the bottom. K times 0.1 to the M. K's cross off. You end up with 1, pretty much. 1 times 2 to the M. Take the log of both sides, which I'm going to do over here. The log of 1 equals M log 2. Divide by log 2, divide by log 2. You end up with 0 equals M, 0 order reaction. So again, this mathematical way, you can always do this, always. Sometimes I do both. Like this one was super obvious. to me right here by inspection, right? So this stayed the same, this doubled, this didn't change, zero order, right? You don't have to do the math way. Sometimes I'll show you one later that you have to do the math way because it's fraction and it's really difficult to see. But you can mix and match, whichever one works for you. All right, so let me just erase all this. So with CO to zero order and NO2, it's a second order reaction. So our order, again, is second order and zero order. So how we write that, as again, this was second order and this one's zero. We don't write zeros because anything to the zero is one. So this is our rate law for our equation or our experiment. So this says determine the rate law and the rate constant. So we need to keep going here. But the rate law is this. That's our rate law. Okay, so how do we find K? That's the easy part. So the first questions we did where you find K, pick any experiment. Doesn't matter which one you do. You will get the same answer no matter what. That's the thing about K. Because remember, K never changes. As long as we don't change the temperature, this stays the same no matter what we put into it. So what do I choose? I always use experiment 1 just because it's the first one and I don't know, I just always do. So you use your rate, which is 0.0021 equals, we're going to find K, and we plug in our NO2, 0.1 squared, and then we just solve for K, equals whatever that ends up being. And just solve for K. So you end up with like divide by 1, 0.0021 K equals times 0.1 squared. And then K equals, I don't know what K equals. But hey, but this is kind of a fun little unit one, right? Because this is molarity per second. And this is squared, so it's 0.1 squared. Fun one. Okay, I'll just put the math here. I'm sure I've got, oh yeah, there it is. So here it is. That's exactly what I just did. And this is our K. So when we put this in, here's our rate law. The more complete rate law would be this, rate equals, that's our K, 0.21. I'm just gonna say 1 over M times S, which is the same thing, times NO2 squared. This is like the more complete rate law because we put in our K, because remember our K does not change. Our K will not change as long as our temperature does not change. So if our temperature does not change, our K will not change. Okay, ready to try one of these on your own? Okay, so by the way, this is exactly what your pre-lab is. Like to the T, this is what your pre-lab is. Okay, so I think I'll give you a minute to try this one. Yeah, so I'm gonna give you a couple minutes to try this one and see where you go. And again, this is literally what we're doing. So what we're doing in lab is we're changing these and then we're actually finding this part. So we're doing this exact same thing in lab, and this is exactly what your pre-lab too is. This is almost identical to what your pre-lab is, by the way. Okay, so try this now. I'm gonna give you a couple minutes and then we're gonna go over this together. Get as far as you can. You might not be able to finish it yet, but just get as far as you can because again, you will be doing your pre-lab on this today. Okay, so try this and we'll go over it in just a couple minutes. Okay, so let's try and go through this one. Even if you didn't get all the way through, that's okay. I think I'm gonna do this one by inspection. And I'll do math for the next one. Okay, so first of all, what are we trying to figure out? What is our rate loss? So remember the rate. Oh, look, moved over. That's even nicer. So the rate is going to be K, sorry, K times the reactants raised to some coefficient. So it's just common to use N and M, but it doesn't matter what you use. You can use X and Y, whatever you want. NO2 minus, and so we're looking for these. So first of all, for NH4, we want to look for NH4 to change, but NO2 to stay the same. So here, well, this is our only choice, right? Because here they are staying the same. Because again, we want to know that any change that happens with our rate is due to the change in here, not this one, right? Because we're trying to figure out what is the order with respect to this specific reactant. Okay, so we're gonna use this one here. So I look here, what happens to this one? Okay, so this one goes up by 3, and this one also goes up by 3. So it's directly proportional. Now I get a question sometimes be like, oh, but it's like 1.94 or 3.27. Close enough. Round and about is good enough here. Because remember, we're measuring this experimentally. It never ends up being perfect. Same thing with your lab. It's not going to be perfect. It's just you're going for the closest one. Now, if it was 3.5, then we'd have to do some more work, and then we'd have to do it mathematically, but it's close enough here. So remember, if it's proportional, so if whatever happens to the change in the concentration of your reactant, if the same thing happens to your rate, that means this is a first order reaction. So it's first order with respect to NH4. Again, why is it first order with respect to NH4? This went up by 3, and this also went up by 3. First order, directly proportional. Okay, the next one is, let's see here. Now we want to keep this the same, but change NO2. Okay. So here we're going to look for this one to not change. Well, it's kind of our only option, isn't it? It's the only one that is the same. So we're going to have to look at 3 and 4 because, again, we want this to be the same. So when we're trying to figure out the order of this reaction, we only want that reactant to change. We don't want any other reactant to change. So we look here what happened. Okay, so this went up by 2, right? And then we look here, 10.8, that's about 2 also. So directly proportional. Whatever happened to our concentration also happened to our rate. Again, first order. So these are both going to be first order. Now you could have done the math to do these, but I did it by inspection. It doesn't matter which one you do as long as it works for your brain. Okay, so this is our rate law. So how would we say this? We would say that this rate law is first order with respect to NH4 plus and first order with respect to NO2 minus. The overall rate would be second order. So we'd say this is second order overall reaction, but first order with respect to NH4 and first order with respect to NO2 minus. So they also want our rate constant. So again, now when we do our rate constant, it doesn't matter which one we choose, like it doesn't matter. Okay, so now I need to draw your attention to something else. So for this part, I didn't talk about this here, but this happens a lot. We'll try to simplify what these look like, but this says times 10 to the 7th. This is actually times 10 to the negative 7th, times 10 to the negative 7th, times 10 to the negative 7th, times 10 to the negative 7th. When we're trying to figure out the order of the reaction, that doesn't matter. But now we need to make sure that we pay attention to what we've got going on over here. It looks like some like horror movie 10 to the negative 7th there. So when we do this, when we do our rate, we need to make sure we put this in here. So what do I mean? So here is our rate. So when we put this in, we can't put 10.8 equals K. This number is not the same as this number. So it doesn't matter when we're figuring out our orders because all the negative 7s cancel out, but it does matter when we're figuring out our rate. And then we just plug these in. So 0.02 10 to the 1, so I'm just going to ignore it, times 0.2 to the 1. So you can pretty much just ignore it, right? So you end up with 10.8 times 10 to the negative 7 equals K times, so that's going to be 4 times 10 to the negative 3. Divide by 4 times 10 to the negative 3. Divide by 4 times 10 to the negative 3. And you get, put this in my calculator, cross off, K equals 2.7 times 10 to the negative 4. And I conveniently left off all my units. So let's just put our units in here. Because that just makes life super fun. So this one is molarity per second. And this one is going to be molarity squared because I multiplied them. So this K's units will end up being m to the negative 1, s to the negative 1. So what is our rate law? Rate equals our K, which is 2.7 times 10 to the negative 4, m to the negative 1, s to the negative 1, times NH4 plus to the 1 times NO2 minus to the 1. Okay, any questions on this? I know it's kind of big. It's a bit big. Any questions on this? All right, I'm pretty sure. Yeah, here's everything I just did. So here's our rate. So here's for NH4, first order. For NO2 minus, first order. And then here I just plugged in. Oh, I always choose the first one when I do this part. When I find my K, I always choose experiment 1. You don't have to, I just always do. You'll notice on all my examples, I always choose experiment 1. So I just use experiment 1, and then I figured out my K. Yeah, units are going to be really important. Yeah, so you're going to have to keep your units in your math when you're doing them for your quiz and for your exam. Yeah, and for your lab. All right. So any questions on this one? Because we're going to do one more of these. And then we're going to look at what your pre-lab would. This is literally your pre-lab. Like, actually, your pre-lab is just like this. Just different numbers.
Professor?
Huh?
We don't have to go to lab today, right?
Oh, correct. Not lab today, for Thursday, but your pre-lab is due today.
Okay.
And it's doing this exact same thing. That's why I didn't make it due over the weekend. Okay. We're going to try one more. All right. So when we look at this one, same thing. They want to find the rate law and the rate constant. So they want the rate law and the constant. So when we do this again, got to get really good at writing this. Rate equals, it's always K times reactants raised to something. Here's my reactants. And I'm just going to do, I don't know, maybe I'll do X and Y this time. Although sometimes when I do that, it freaks people out. So I'll say M and N. Again, doesn't really matter which ones you do. Okay, so let's take a look here. All right. So we can do this by inspection. Absolutely. So if we want to do N first, we're looking for O2 to be the same. Well, this is our only option, right? So we look here. That one's not so super obvious. You could probably do that by inspection. Right, that looks like a 4 and 4, so this might be first order. I'm actually gonna put this on my calculator. So all you do is divide them to see. So it looks like first order to me. So 0.04 divided by 0.01, 4, 500 divided by 125, 4. Yeah, first order, because they both went up by 4. So this one up by 4, and this one up by 4. So it's first order with respect to N2. Okay. All right. So now let's figure out O2. So for O2, this is my only choice, because remember, I want this one to be the same. The only change I want to be happening is due to O2. So I have to choose the experiment where these two stay the same. So see how these are the same? That's why I have to choose 1 and 2. So now when I do this one, put that in my calculator. This doubles. This doesn't double. It doesn't double. It's not the same. I'm not really sure what that is. I got a fraction. So point, let me see, what did I just erase it? So this one up by 2. This one by, I got 1.4. Okay, yeah. So remember what I said, like about and around? That's not close. Like that's not close. It has to be like 1.1, 2.1 or 1.9. 1.4, that's smack in the middle. You have to math that. So remember how I said like you can do it by inspection like almost all the time. Sometimes you have to math it. When you get something like that, you have to math it. And what do I mean by math it? You have to do what I did the first part. So let me see if I have, no, don't really have a lot of room to do this, but I'm going to do this here. Okay, so I need to math this to figure out the order of the reaction because 1.4 is not helpful for me. So I'm going to do experiment 1 over experiment 2. And I'm going to do it rather small right here. So again, some people really just like doing the math way. So I'm going to do number 1 over number 2. That's what I'm going to do here. So number 1 is just 707, the rate. 707 equals K times 0.02 to the M. And again, this is going to cancel out, so I'm not even going to put it in. And then I'm going to do experiment 2. 500 equals K times 0.01 to the M. My K's cancel out. I already know this is 1.4. My calculator says 1.414. That did not end up nicely for me. And then 0.02 divided by 0.01, that's just 2. 2 to the M. So we take log of both sides. So log 1.414 equals M log 2 divided by log 2 divided by log 2, 2, and I end up getting 0.499 equals M. That means M is 1/2. This order is 1/2. Yeah, That's not a fun one. So this n right here is 1/2. So how I would read this, this is my rate law. First order with respect to N2, half order with respect to O2. The overall order is literally 1.5. So 1.5 order reaction, or 3/2, however you want to say it. That's the overall order. So you can have, and you're going to see, we're going to have like negatives next week, or on Thursday, we're going to have like crazy fractions, plus positive fractions, negative fractions, all sorts of crazy stuff happening. But you can have, usually it's 0, 1, or 2, but you can have not 0, 1, or 2. You have to tell those literally by doing the math part. And again, some people just like to do this every single time. Whichever one, you could do some, whichever one floats your boat is okay to do. Okay, so now I've sort of run out of room here. So to figure out our K, which I figure at this point, we should be good with our K. So to figure out our K, so question, how did I get the half again? Okay, so the half came right here. When you divide this, you get 0.499, which equals 5. That's where it came from, right? And so what did I do here? This step to this step. I just took the log of both sides. So when you take the log of this side, I'm going to do this in a different color. Do it blue. So when you take the log of this one, it just becomes log of 1.44. And this one becomes m log 2. And then divide by log 2 on both sides. Take this, and you get 0.499, which is 0.5, which is 1/2. So m equals 1/2. All right, any other questions on this part? Other questions? Okay, so to do our rates, and feel free to ask questions at any time. I'm just gonna always, you don't have to use experiment 1, I just always use experiment 1. So our rate is 7.07 meters per second. Checking to see, is there any like exponents, anything in here? Nope, just straight 707 equals K times N2. So 0.04 to the 1 times O2 to the 1/2, which, by the way, in your calculator, do 0.5, it makes it so much easier. Don't put it 1/2 in there. Too many fractions, your calculator goes bonkers. So I'm not going to solve this one just because we've done this 100 times, but not 100 times, we've done it a bunch, and then we solve for our K. All right, so here is my math again. So here's my first one, which was first order. And here's the second one, which ends up being half order. So our overall order ends up being 1.5 or 3/2. Okay, so our rate law, again, this is exactly the math I just did. Our rate law ends up being this. Now, you gotta love the units, because I actually solved the units on the next one. So when we put these units in here, remember this one is meters per second. I mean meters, molarity. This one's molarity. And this is molarity, but this molarity to the half. So we have kind of a weird, so by the way, when I do my units, I literally do them like this and just do my math with my units. What does that mean? I will literally take this, and I'm solving for K, so I'm going to divide this by molarity times half a molarity. Molarity over molarity times molarity 1/2. These two cancel out. And I end up with, this is s to the -1, and this is on the bottom. So it's m to the -1/2. This is the same thing as 1 over s to m to the 1/2. So like I said, when I do my units, I don't do them with my problem because it just, sometimes I mess up my numbers. I just do them individually. So let me just do that one more time so you can see how I did that. So how did I know the rate was this? Let me just go back here. It tells you reaction rate, molarity per second. These little parentheses, these little, I don't know what you call those always are molarity. So this is always molarity, this is always molarity, this is always molarity, it's always molarity. So when you plug it in, rate, my unit is molarity. I'm gonna try it like this for you, over seconds, equals molarity, and then molarity to the 1/2. So now when I divide this, I'll show you why I did this in a second. This is molarity per second. When I divide these two, they go on the bottom, molarity and molarity to the 1/2. This molarity crosses off with this molarity, and so that's what we're left with. This is the same thing as this. So that's the units of our K. And however you want to get those units is fine. They just are wacky. And so you kind of have to get used to kind of doing some crazy things with your units, just keeping track of them. And like I said, I always do them later than earlier. Just for my brain, it works better. But if you want to do them throughout the math, you can absolutely do that. It's probably faster that way. So here we are. This is that when you do the division, this is what you actually get. And then those are our units. And again, remember, this is just the same thing as 1 over m to the 1/2 times s. We tend to always write them with their exponents and never use fractions with our k's. But this is the same. These units are exactly the same.